Let's talk about the spatial statistics with respect to GIS, that is Geographical Information System. And these statistical options tends to limited to most GIS applications. And we'll look at spatial statistics in general terms and conclude with the review of the software which are available for these spatial statistics. So let's start with the basic concepts. The spatial statistics differ from ordinary stats by the inclusion of locational properties. So this is very important. Ordinary versus inclusion of locational properties. This makes spatial statistics more complex, as we have locational properties, and Bailey and Gatron provide an accessible introduction. So there are 4 categories: point pattern data, spatially continuous data, aerial data, interaction data. So obvious correspondence with the conceptual model is been seen. So what will be the scale levels? Attribute data can be classified by measurement scale. We know that measurement scale are nominal, ordinal, interval. So nominal is 1 or 2, ordinal means 1, 2, 3, means good, medium, poor. Interval means degree centigrade, 10 to 20, 20 to 30, this kind of interval. Okay, there are the techniques which were followed by these gentlemen. They proposed visualization, exploration, and modeling. And this is involved in all statistical inference and hypothesis testing. Random variables, stats model deal with phenomena that are stochastic. What are stochastic? That are subject to certain uncertainty. So a random variable, say y, has values that are subject to uncertainty, that is but may not necessarily be random, And distribution of possible values refers to as probability distribution. These are the possible value distribution, which is represented by Fy, where y is, as we have known, the random variable. So random variables may be discrete, that means precise values, or continuous, like the sinusoidal waves. So the probabilities will be like this: probability that y is between a and b, certain a mark, b mark. So if y is discrete, it will be sigma. We know that for adding discrete values we use sigma, for continuous values we use this sign, we call it integration. So discrete values, we start from a to b, and this function we add, and again for y, when it is continuous, that is probability density, we integrate it from a to b, same function with respect to dy. And the cumulative probability or distributive function fi is given by fiy, same thing, in capital, and we start from minus infinity to y, and here also this is the cumulative probability, again through integration minus infinity to y. So expected values, the expected value of y is its mean, ey, mean, because we are summing it, and this will be sigma minus infinity to infinity and minus infinity to infinity. This is sigma, this is integration. And expected value of function y, say gy, is, we have e of gy, that is expected value of gy, that will be gy into fy gy, and e gy will be minus infinity to infinity gy into f, same, this we have known it for discrete, for continuous, and variance will be the value and expected difference of that square and that summation. So the square root of this will be standard deviation, as we calculate standard deviation, sigma. The joint probability can generalize to situation where there is more than one random variable. So joint probability distribution will be fxy. See, we have joint probability distribution. Covariance will be again covariance of x into covariance of y, xy, and then sigma. The correlation will be covariance of xy divided by standard deviation of x, standard deviation of y. And independence, Neither variable affects the other, so joint probability is product of individual probabilities fxf, fyy. So statistical model, a statistical model specifies the probability distribution for the phenomena being modeled, and if modeling ozone levels in a region R, we would have a probability distribution for each location S, where S is a 2x1 vector of xy coordinate pairs. So individual points can be referred to as S1, S2 and so on. The complete set of random variables may be referred to as the spatial stochastic process. So the probability distribution for near points will probably be more similar than the distant point. So our random variables will be probably not be independent. And specifying model, to specify a model we need to specify its probability distribution. For the ozone model we would need to specify the joint distribution of every possible subset of random variables. For example, for a fair die there are 6 outputs, so f, y, y, v1 by 6, and for more complex models we use observed data. These are the observed data. And these data are a realization, that is an outcome from the joint probability distribution y1, y2. This capital we have already learned. And one set of data does not get us very far. Even with more data observation, we must make reasonable assumptions based either on theory or prior observations. And assumption may be expressed in general terms, that is normal distribution or regression model with certain specified parameters. Model can be fitted using observed data to estimate the parameters, and after evaluating the model we may decide to change it general form. So taking a regression model to illustrate, to model our ozone data, we might make the following assumption: random variables. This is why S is stochastic, S belongs to R, are independent, they have the same distribution but different means. Their means are a simple linear function of location, say E, Y, S, B0, B1, S1 plus B2, S2, as we have taken S1, S2 and so on. And each YS has a normal distribution about this mean with the same covariance, say, sigma square. These assumptions would enable us to estimate the parameters from the available data. So maximum likelihood, the most frequently we use is maximum likelihood. We can write down the general form of the joint probability distribution. Example, for example, we have f y1 to yn theta, where theta is a vector of parameters, that is b0, v1, till sigma square in our regression model. Given that we have actual values for y1 to yn, this joint probability distribution is the probability of getting these actual values. So this is referred to as the likelihood and would usually be denoted by L for likelihood y1 to yn and theta. Our objective is to identify the parameter value theta, this value that maximizes L, and in practice we usually maximize the logarithm log likelihood denoted by L. So parameter estimation, this is the basic approach, but the actual estimation may be complicated. So parameter estimation of our multiple linear regression involving assumptions of independence, normal distribution and equal variance reduces to using the method of only ordinary least squares. So relaxing the independence and equal variance, we can still use generalized least squares. Standard errors provide a measure of the reliability of each parameter estimate, and likelihood ratios can be used to compare alternative models. Then coming to hypothesis testing, it entails comparing the fit of two models, one of which incorporates assumptions which reflect the hypothesis and the other incorporating a less specific set of assumptions. So all modeling inevitably involves some assumptions that the phenomena under study. Hence, hypothesis testing will always involve comparison of the fit of the hypothesized model with that of a alternative which also incorporates assumptions that with the of a former more general value and nature. In spatial data modeling, spatial data often exhibit spatial correlation. This is very important. This is also called autocorrelation. Assumptions of independence may therefore be unrealistic. So you can make a distinction between first order effects and second order effects. First order effects are the variation in the mean due to global trend, and second order effects are casual by spatial correlation, and can illustrate using energy of iron pairings and magnets. and real world patterns are also often an outcome of mix of first and second order effect. So to allow the second order effect, the spatial models may need to assume a covariance structure. The second order effects may be modeled as a stationary spatial process, that is, its statistical properties, mean and variance, are independent of absolute location, and covariance depends only on relative location. The process is said to be isotropic if it is stationary, and covariance depends only on distance and not direction. So if the mean variance and covariance drifts over the study area, then the process exhibits non-stationary or heterogeneity. Heterogeneity in the mean combined with stationarity in second order effect is a useful spatial modeling assumption. Modeling of a spatial process often tends to proceed by first identifying any heterogeneous trend in mean value and then modeling the residuals or deviations from this trend as a stationary process. So geographically weighted regression. Covariates are often incorporated in a multiple regression model taking the general form. This is the form, and the model assumes the coefficients are homogeneous or stationary. So this gentleman proposed an alternative model. This is the alternative model. See, we have some additions here to allow the model to be fitted in. It is assumed the parameters are non-stationary but are a function of location. So parameters can be mapped. Point pattern techniques. Bailey and Gattel discussed various techniques organized by data type. So point pattern techniques include quadrant analysis, kernel estimation, nearest neighbor analysis, and K functions. So normally used to test null hypothesis of complete spatial randomness, that is homogeneous Poisson process, but can also examine heterogeneous Poisson processes. Spatially continuous data, the techniques used to explore field data, sometimes referred to as geostatistics also. So we have spatial moving averages, trend surface analysis, Delaunay triangle, tins, Thiessen polygons, kernel estimation, variograms, covariograms, kriging, PCA, factor analysis, procustis analysis, cluster analysis, and canonical correlations. Coming to area data, techniques for analyzing aerial data, that is polygon, include spatial moving average, kernel estimation, spatial autocorrelation, spatial correlation, and regression. So generalized linear model provides a family of techniques of dealing with special types of data, that is counts as in Poisson regression and proportion as in logistic regression. So Bayesian techniques often used to model rates based on small numbers. As spatial interaction data, techniques for modeling spatial interactions are most based on some variant of the governing model. And this postulates that the amount of interaction between two places is a function of their sizes and is inversely related to the distance between them. So the software which are providing this are ArcGIS, Idrisi, and S+. R is a specific statistic software, and Bugs software for Bayesian statistics. Thank you so much. Take care of your